Welcome to this explainer. We're diving straight into the Accelerated Algebra 1 enrichment today, specifically Unit 10, Lesson 4, Rational Numbers Data Check. So if you're looking for that extra challenge, something that really pushes beyond standard grade-level expectations, you are in exactly the right place. Today we're unpacking multiple representations, proportional reasoning, and a real-world 7 to 8 rice per serving model. It's going to bridge us right into higher-level mathematics. Let's get right into it.
Here's our roadmap for today. First, the enrichment boundary, followed by our goals and vocabulary. Then we'll hit the rice model, explore multiple representations, correct a major misconception, and finally, wrap up with a data check.
Section 1, the enrichment boundary. Above grade 7 core.
Okay, so first things first, we have to be clear about what this material actually is. It's strictly an optional challenge for ready students. You can think of this Unit 10 Lesson 4 data check as an above grade level extension. Now, it's perfectly designed to introduce advanced proportional reasoning, but, and this is a big but, it should never replace your grade 7 core foundations. Make sure you've got a rock-solid grip on basic rational numbers and foundational ratios before tackling this. It's really all about building upward from a strong base.
Section 2, goals and vocabulary, our math toolkit. We've got 4 main learning goals today. We are absolutely laser-focused on using multiple representations to truly understand rational number quantities. So rather than just blindly crunching numbers, we're actually going to apply proportional reasoning to a very specific real-world scenario, the 7 to 8 rice per serving model. By the end of our time together, you're going to be able to seamlessly scale these quantities up or down no matter what the situation throws at you. Now keep these critical vocabulary words tucked in the back of your mind. We're talking proportional reasoning, quantities, and multiple representations. Understanding how a scaling factor interacts with a ratio, well, that's literally the primary mathematical tool we'll be reaching for constantly as we analyze our data check. Grasping these terms inside and out just makes everything that follows so much easier.
Section 3, the rice per serving model, proportional reasoning.
I want you to imagine we're in the kitchen. We're looking at a recipe that calls for a highly precise ratio to achieve that absolute perfect texture. 7 parts water to 8 parts rice. This right here is the 7 to 8 rice per serving model. It gives us a really tangible, concrete way to think about rational numbers. Every single time you pour in 7 units of water, you strictly need 8 units of rice to keep the whole recipe balanced. The real magic, though, that happens when we need to change the size of the batch.
And this is exactly where proportional reasoning shines. Say we're cooking for a massive crowd. We scale that 7 to 8 ratio up using rational numbers. Let's say our scaling factor is 2.5. We just multiply both the 7 parts water and the 8 parts rice by that exact same rational number. Maintaining that multiplicative relationship guarantees our final quantities are perfectly proportional. It doesn't matter if we're making half a serving or 100 servings. The math just works.
Section 4. Multiple representations. Leveled practice.
When we model this race-to-water ratio, we don't just use one method. We use tables, graphs, and equations. These multiple representations, they all tell the exact same story, just in their own unique way. A table helps you quickly spot step-by-step patterns. A graph visually shows you the constant rate of change, like a perfectly straight line shooting right through the origin. And an algebraic equation? Well, that's the ultimate shortcut to calculate any serving size instantly.
Let's actually walk through a leveled practice scenario together. If we know the base ratio is 7 parts water for every 8 parts rice, how do we write an equation for water, we'll call that W, in terms of rice, represented by R? First, we find the constant of proportionality by simply dividing the water by the rice. That gives us 7/8. Boom. So our final equation is just W equals 7/8 times R.
Section 5, common math mistakes. Avoid these traps. Now pay close attention, because the hardest part of proportional reasoning almost always stems from one deep misconception: confusing additive and multiplicative scaling. When trying to increase our 7 to 8 recipe, so many students mistakenly just add a number. They think, oh, I'll just add 2 cups of water and 2 cups of rice. No way! That completely destroys the ratio. Ratios absolutely require a multiplicative scaling factor. You must multiply both quantities by the same rational number to keep everything perfectly balanced.
Section 6, check for understanding. Practice questions. All right, time to put you to the test. Let's jump straight into the first 2 questions of our 5-question data check. Question 1. Using our trusted 7 to 8 water to rice model, how much water is needed if you happen to have 24 parts of rice? And question 2, express the ratio of water to the total mixture as a single fraction. Go ahead and take a quick moment to mentally calculate both of those.
Okay, let's see how you did. For the first one, since 24 is exactly 8 times 3, we know our scaling factor is 3. Multiply those 7 parts of water by 3, and you get 21 parts water. Nice and easy. For the second question, the total mixture is 7 parts water plus 8 parts rice, giving us 15 parts total. Therefore, the fraction of water to the whole shebang is 7/15.
Moving right along to questions 3 and 4. Question 3 asks for the inverse equation. How do you find the amount of rice, R, based on the amount of water, W? And question 4, thinking back to our multiple representations, if a graph plots water on the x-axis and rice on the y-axis, what is the exact slope of that line?
Let's break these down. For number 3, to find rice in terms of water, we just use the reciprocal of our previous constant. So the equation is R equals 8/7 times W. Now, for number 4, remember that slope is always the change in y over the change in x. With rice on the y-axis and water on the x-axis, the slope is perfectly represented as 8/7. Notice how the equation and the graph completely mirror each other? Pretty cool.
Let's wrap this up with the grand finale, the last question of our data check. A chef uses 3.5 liters of water for a specialized batch of this exact recipe. Using our foundational 7:8 ratio, how many liters of rice are required? Think carefully about your rational number scaling factor here.
So to go from 7 parts water to 3.5 liters, our scaling factor has to be 1/2, or 0.5, right? We just apply that exact same multiplicative factor to the rice. 8 multiplied by 1/2 gives us a perfect 4. The chef requires exactly 4 liters of rice. Huge congratulations on working through this Unit 10 Lesson 4 Enrichment Challenge. You guys just crushed proportional reasoning, manipulated rational number quantities, and completely successfully analyzed that real-world rice model using multiple representations. But before we go, it does leave us wondering, how will these exact foundational skills come into play when we finally encounter those massive, complex quadratic equations and polynomial functions later in the year? Keep these analytical skills sharp, my friends, because this is just the beginning of your algebraic journey. Thanks for hanging out and learning with me today.